Welcome back to the channel everyone. Today we will discuss a problem from gravitation chapter, and I have picked up this problem from one of the Allen's test papers. It's a quite interesting problem. We will see that in the solution. So let's get started. It's a paragraph type question. Obviously you can see there is a paragraph and two questions are based on this same paragraph. So the question states that on a certain planet, which is a uniform solid sphere of mass capital M and radius capital R, due to rotation about its polar axis, ratio of maximum to minimum values of apparent acceleration due to gravity at the surface is 3:2, and we're given a diagram. So let me read out the questions as well together first. What is the length of a geostationary satellite which is a vertical rigid rod with its one end suspended in air near Earth's surface? If the answer is PR, I mean P times R, then mark P. And the second question is asked about if the rod is suddenly stopped and released, then immediately after release, just before collision with Earth, what is the ratio of tension in the rod at the points of trisection? Closer point of the to the Earth to further. Okay. So first we need to find out the length of the geostationary satellite, which is obviously in a form of rigid rod. So we are given a data here that due to rotation, obviously the G will vary on the surface of Earth. We also study that variation of G with height, depth and rotation, right? So it's the application of that concept. Apparent accelerations maximum to minimum ratio is 3:2. Obviously you must be knowing that maximum acceleration due to gravity will be at equator and it will equate to G, where I have chosen G as G m upon R square. M is obviously mass of the planet and R is the radius. And at pole it will be minimum, right? Minimum of G, apparent G. So apparent G will be G minus omega square R. Okay. And obviously the same G minimum will occur at this pole as well. I have not shown. Okay. At equator it's maximum, and as you gradually go to the pole it will keep on decreasing and it will subtend the minimum value at pole, right? So just using the given datum that G upon G minus omega square R is 3 upon 2, just cross multiply and rearrange the terms a bit, you will end up getting this result, right? Relation in G, R and omega square. So you'll use this equation later on. Let's keep it aside. And further, this one is the planet and this is the geostationary satellite. So okay, one thing I should have clarified here, that here it is a major hint given in question, right? If I was the question setter, I would not have given this information, that in case of geostationary satellite, the satellite and Earth both having same angular velocity. Because what happens, sometimes students just mug up that at 36,000 kilometers from Earth you place a satellite and that will act as a geostationary satellite. So that's not complete concept, right? Because the planet can vary, the radius can vary. What is the concept? It is that geostationary satellite means when you sit on the frame of the planet, you will observe the satellite as static. And to be that, what should be the condition? Now, the omega of planet and satellite should be same. If the angular velocity is same, you sit in the frame of anyone and you will obviously always see the other one in your line of vision, right? Let's say this one is the planet, this itself is rotating about its own axis, and here is the satellite revolving around it. So if both the omegas are same, you will always see in the same line of vision, right? If here is the if you are when you are here, you will see the satellite here. When your line of vision is this, you will see the satellite here, right? So that's the concept of geostationary satellite. So it is given already in question that two omegas will be same. So that's one clarification. Next, moving on to the next part. Yeah, I have assumed, let me write it here, I forgot, right? Mass of the rod, total mass of the rod is capital M, sorry, small m. Capital M is the mass of the planet. So in case of rod, I need to find out the force of interaction, I mean the gravitational pull of planet on that rod, right? If it was a spherical body, then you can directly do the g cap m1 m2 upon r square, where r would have been the radius, sorry, separation between the two spherical bodies. But as it is a rod, you can't do that directly. You have to take elemental part and find out the elemental force on that one, and then integrate to get the total force on the rod. So to do that, I have taken a small differential element of dx length at a distance of x from the center of earth, and its mass will obviously be m by l upon dx, as small m was the total mass of the rod and l was the length of the rod, I have assumed, times dx is the length of that small differential part. So df will be g capital M into, this is the dm part, mass of the differential element, upon x square. So you just integrate this one as a function of x. So what's the limit of x? This one is one end of the rod, it is almost at the surface of earth, that means at a distance of r from the center, and this end is almost r at r plus l length from the center of the earth. Okay, so limits will be from r to r plus l. So putting the limits, we'll get force expression something like this, and you divide the force upon by small m, the mass of the rod, you will get the acceleration of center of mass of the rod. So as the rod was in rotational motion, it was having an omega, I mean the angular velocity omega, and here was the center of mass of the rod. Center of mass of the rod will obviously be at the center of the rod, as the for uniform mass distribution. So this length will be L by 2, and let's say this one was the planet. Obviously a very bad diagram, but just for understanding I am drawing this. And this one was the radius of earth. So basically the center of mass was at a distance r plus L by 2 from the earth center. So you can assume that a small m mass was revolving around the center of planet with the angular velocity omega at a radius of r plus L by 2. So from this understanding, you can clearly write that acceleration of center of mass of the rod will be omega squared times r. In rotational motion, we study that the centripetal acceleration is basically omega squared times r. So center of mass is at a distance r plus L by 2 from center of earth or planet. I may sometime call it earth because that's the convention, but you just assume it at the planet as the planet that has been mentioned in the question, right? So we'll equate ACM with omega squared times r plus L by 2. Now again it's just a simple calculation, and yeah, we have used the equation 1 result here. I have marked it, right? Yeah, that omega square was g upon 3r, so I have put that result here, and I have also put g value as gm upon r square here, g capital M upon r square. And after putting this, you will get some terms cancelled, like gm, one r gets cancelled, so this one will be r square. Now just keep 3r squared terms this side and multiply the rest of the terms, you will get something like this. Rearranging, you will get a quadratic equation in r or L. I have shown in r, you can also solve it in L as well. After factorizing, you will get two roots. Definitely this one is not possible because length cannot be negative, so L is r, and we are told that L was p times r, and we have to report the value of p, so p is 1, right? So the answer of first part should be 1. Let me write it here. Yeah, p is equals to 1. This is one answer. Moving on to the second question, it is said that the rod is suddenly stopped and then released, and we have to find out the ratio of tension at 2 points of trisection. So let's say here the rod was just stopped and released, so just due to gravitational pull, the rod will start to move towards the earth, and we'll find out the tensions at point B and C. We are supposed to find out the ratio at B to C, because nearer point to further point, that was our sequence given in the question. So what will be the acceleration of the rod, or you can call it the acceleration of center of mass of the rod. Anyway, it is actually same. When rigid rod is in translational motion, let's say this rigid rod is accelerating with A, then all the points should have the same acceleration of A. Otherwise it can't be a rigid rod, right? So if I call it as ACM or A, whatever it is same, each of the points on the rod will have the same amount of acceleration. So in case of a rod and sphere system, I guess we find out the force of interaction here, right? Yeah, this one was our force of interaction, right? So we'll just put the value of L here. L, we have already find out that L is equals to R. So if we put L equals to R, this one is acceleration. Obviously there was one mass term in force expression. In acceleration there will be no mass term. So this is G capital M upon 2R square is the amount of acceleration of the rod. Now we will just write the equation of motion for two parts. First we will do for part AB, I mean only this one part. So if you just observe the FBD of this part, you will get a gravitational pull of earth and there will be one tension. So if this is the AB part, there will be one gravitational pull, let's say FG, there will be one tension T1. So what will be the FG? Again the same expression for sphere and rod system. That one was G capital M, and here M by 3 obviously, because AB is 1/3 of the total rod, and R plus this one, remember this one was the L length, right? Length of the rod. Rod length has also decreased to R by 3 as it is 1/3 of total. So just putting the values, we'll get this. This is gravitational pull minus tension, mass of the rod M by 3 times acceleration of the rod. This one G capital M upon 2R square. Again, I'm not explaining these calculations, these are basic stuffs. You will just get this result, T1 equals to G capital M small m upon 12R square. Now we'll do the same thing for part AC, because we are doing for two parts separately because we are trying to involve the T1 and T2 terms, right? T1 is the tension at B, so we should have used the rod AB or BD as per our convention. And if we have to involve T2 term, we have to use the rod AC or CD like this, right? As we are having the expression of sphere plus rod force system, when the rod's one end is at A, so it will be conventional if we deal with a certain rod plus sphere system where the rod's one end is at A, then we need not to calculate again the force of interaction and all these things. That's why I'm doing for AB part once and now for AC part, right? So this one was one clarification that how you should approach problems, right? So let's do the same for AC part. For AC part, again you will get a gravitational pull towards the earth and you will get T2 tension away from the earth or planet. I have already clarified that one. Okay, so yeah, here is the gravitational pull part. This one was the mass of rod. Yes, here AC rod is 2/3 of total, so mass will also be 2/3 and length will also be 2/3 of total. Here is the mass, here is the acceleration, mass times acceleration. This one is the net force side. So just calculate these things and you'll get T2 as G capital M small m upon 15R square. And our final answer will be T1 upon T2, and that is coming out as 1.25. And this is our answer for second part. So let me go back to the question and just write it here, that our answer is 1.25. So that's all for this problem. Yeah, you can call it a bit calculative, but it tests your concepts as well very much, right? So I guess it's a quite good problem to test your concepts, and I hope you have enjoyed it. Thank you. That's all for today.